Hello, welcome to another session on Economics 296U. I'm not so sure that the webcam is working properly, so you'll have to excuse me because I'm going to have to be doing 3 or 4 things at the same time. As a result, I don't think that we're going to have a very long session. However, I wanted to share with you a few things about energy that probably you might not be able to find on your own. The first thing that I want to do, I think we might have mentioned once before, is that energy normally is measured in quads. So in the United States in 2011, which is the last year for which we have exact data, we've produced practically 100 quads, and the quad is 10 to the 15 BTUs. A BTU is the energy that is required to raise the temperature of a pound of water by 1 degrees Fahrenheit. And so that will give you an idea about really the amount of energy that we're talking about. The thing that I would have wanted to show you, but I can't unfortunately because of these technical problems, is a chart that would show you all of the inputs, of the primary inputs of energy in the United States and all our outputs. So let me see if I can describe it to you very quickly and see if you can keep track of it. The primary inputs are essentially really solar energy, nuclear energy, hydro, wind, obviously natural gas, coal, petroleum, and biomass. The largest of these is really the petroleum, followed by natural gas and coal. But what is really fascinating, and that most people do not pay attention to, is that out of the 100 quads that we produced, the solar accounted for only 0.158. This is a 1/6 of 1% of the energy that was produced in the United States was from solar. In wind, we did a little bit better. It was just over 1%. I think we produced around 1.17 quads. And when I say 1%, I'm really assuming that we produced 100 quads. But if you want to be precise, we produced 97.3 quads. So yes, we did produce a little bit more than 1.1%, maybe 1.2%, and so on and so forth. And so as a result, when people speak about the renewables really being able to substitute for the fossil, as you can see, we have a very, very, very long way to go. It's not going to happen in a year or two, or even in a decade or two. Could it happen in 30 or 40 years? Well, yes, possibly. There are right now, New York State around 10 days ago issued a new study in which they plan to become totally fossil-free by the year 2030. In theory, it is doable, but speaking about theory is one thing, and then putting these things in practice is another. Now, before we really put you all to sleep, the thing that I wanted to really stress is that, okay, out of all of these primary sources of energy that amount to almost 100 quads, what do we use? Well, we use, believe it or not, only around 40%. Actually, a little bit more than 40%. So what happens to the other 58 or 60%? That is always a waste. Why is it a waste? Well, we might have mentioned before, or you might have run into the term during some of your readings. That's because of the second law of thermodynamics. It is part and parcel of the game. There's nothing that you can do about it. We will produce certain amount of energy, but we will not be able to use all of it in order to do work. So around 60% of the energy that is being produced is being wasted. Now, can we do anything about cutting down that waste slightly? I am not so sure that we can, but let's assume that potentially we can cut down on that waste a little bit. But we will not be able to cut down on the waste by much, because it is part of the natural laws of science. That is the way the world functions. You produce energy and then you convert it into work, but you never get out of work as much as the energy that you have produced. So technically, and I'm going to definitely oversimplify, it's as if we produce 3 BTUs and we use only 1 and the other 2 are wasted. And that is because of the law of the second law of thermodynamics, which is commonly referred to also as being entropy. So the energy of the system, the entropy of the system will keep on expanding. Energy can never be created nor destroyed. But as we use it, we will have less of it, because the 2/3 that is being dissipated will never be able to, we will never be able to recapture it in order to use it one more time. The only other thing that I wanted to try and bring out will be some calculations that are very difficult normally for people to find out. Not because the calculations themselves are difficult, but you've got to do lots of digging in order to find them. Whenever we talk about energy these days, one of the first things that comes to mind will be that people start speaking about the efficiency and how is it that we're going to solve all our problems, and especially the climate change problem, by having electric cars. Now, is an EV really a zero emission? Well, yes, if you go ahead and buy it, you as a consumer, you're not going to be emitting directly when you drive that particular vehicle any CO2s. But what about the energy that's going to be required in order to drive that particular vehicle? Let me give you a very simple example. In the United States, and we have really only 2 EV cars, we have the Volt and we have the Leaf. It takes approximately 3 kilowatt hours to drive 1 mile. But every kilowatt hour, actually, sorry, it's exactly in the reverse. It takes 1 kilowatt hour to drive 3 miles. So every single kilowatt hour in the United States that's produced, the national average for the national grid is 1.2 pounds of CO2. Therefore, in order to drive 1 mile, you need 1/3 of that 1.2, which really turns out to be 0.4 pounds of CO2 per mile. Well, how does that compare to gas cars? Well, and not natural gas, I mean regular gasoline cars. Every single gallon of gasoline produces 19.6 pounds of CO2, approximately 20. So, if you have a car that can get you 50 miles per gallon, then that would be equivalent to 0.4 pounds of CO2 per mile. So notice what we're saying is that the maximum cleanliness in terms of emissions of CO2, given our current national grid of creating electricity, of generating electricity in the United States, is to produce 0.4 pounds, which is around 500 grams, a little bit less than 500 grams of CO2 per mile. But if you have a car such as the Prius, which is really a gasoline car, that gets 50 miles per gallon, then that also is equivalent to 0.4 pounds of CO2 per mile. So really, even if all the cars are going to be transformed tomorrow into electrical vehicles, the most that we can do, or the most that we can say, is that the efficiency of emissions will become really only 0.4 pounds per mile of CO2. Now that doesn't sound probably very bad. It will be a slight improvement, but it's not really a great improvement. Or at least it's not as big of an improvement as to be able to significantly change the concentration of CO2 in the atmosphere, because that CO2 really lives on for years. So even if we are to cut down on the CO2 emissions substantially, it is sort of in the pipeline that the concentration of CO2 is going to increase. And the 2 degrees centigrade, i.e. almost the 4 degrees Fahrenheit, are already in the pipeline. So you have all of these organizations that speak around about 350. Let's say we've got to try and keep the concentration at 350 in order to prevent the 4 degrees centigrade instead of the 2 degrees centigrade. But we are already almost at 400. Last February we were at 396.4 parts per million of CO2 in the atmosphere. So the electric cars are good, but even if we get them, they're not really a tremendous improvement on what we have. And even then, if you have a magic wand to transform all our vehicles or our fleet overnight into EVs, yet it wouldn't really place a major dent in the concentration of CO2. So as you can see, the problems really that we are facing, especially from the emission from the fossil fuels, are really tremendous. And I know, since I'm not so sure that any of these things are going to work today because of the problems I'm having with this webcam, I'm going to make it short and say until I see you next time. Bye-bye.